Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be doing our brief aside by looking at organic molecules. And one of the reasons I really like emphasizing organic molecules is that in the kind of day-to-day understanding how we interact with chemistry, it usually occurs through these sort of organic molecules. And one of the big things when I'm talking about organic molecules, what I'm really going to be talking about is molecules that are primarily composed of carbon and hydrogen. Really, the general definition of an organic molecule is that it contains carbon and it isn't CO2, carbonate, or some variant thereof. Everything else, as soon as you get a carbon-hydrogen bond, you've got an organic molecule. And this goes through a huge range of everyday life. And this includes, for example, if we start throwing in some nitrogen and oxygen, ta-da, we suddenly have amino acids, and this is where you get your proteins. A little bit of sulfur, and you have the complete set of amino acids. We also have plenty of drug molecules like morphine. Throw in some phosphorus, and you have nucleic acid, which is required for DNA. So if you want to understand life or cooking or pretty much anything interesting about chemistry, you have to be familiar with the basic structure. And before we go in talking about chemical reactions, I want to make sure we acknowledge what sort of molecules we can use. So the simplest of organic molecules are called alkanes. And one of the big defining features of an alkane is all they have is carbon and hydrogen, and that is it. The simplest form is called a hydrocarbon. Again, because we have hydrogen and carbon. And if we have only single bonds, this is called a saturated hydrocarbon because we put on as many possible hydrogens as we can around a given set of carbons. So one of the cool things about these alkanes or saturated hydrocarbons is they have a very constant molecular formula. If you know how many carbon atoms you have, you can double that and then add 2, and that's how many hydrogen atoms you can get. And the reason why is because if we have the 2 carbon atoms on the end, they're going to have 3 hydrogens. Everybody else will have 2 hydrogens. And so you have a very predictable molecular formula. And as a result, we tend to have very predictable names. So these basic saturated alkanes are named based on the number of carbons present in the molecule. So if you've got 1 carbon, this gives you meth. If you've got 2 carbons, this gives you eth. If you have 3, prop, 4, bute. Then once you get 5 and on, then you can just use your geometry. Pent, hex, hept, oct, non, and dec. Gets a little bit confusing after that point, but one of the big features is when we're looking at alkanes, so again, these saturated carbon containing molecules, they'll always have that same ending, ane. So meth, 1 carbon, ane. I've got a 1 carbon alkane, and then 2, 3, and so on. Now, one of the things that I personally had the hardest time in chemistry was how to keep these first 4 groups straight. How do I know meth, eth, prop, and bute is 1, 2, 3, and 4? Well, for there, I've got a great mnemonic. Meth eats people's brains, and you won't be able to forget it. So methyl comes first, then ethyl, prop, and bute. However, one of the big things is as we get these longer and longer carbon chains, I have more and more ways I can potentially arrange, say, 4 carbon molecules. And so one of the things, once you get to butane, is we can have all of our carbons in a nice straight chain, or they can be what are called branched, and they go off in these countervailing directions. Note that you still have the same number of carbon atoms and the same number of hydrogens, but the arrangement is slightly different. And to convey this, we have a common name called isobutane. However, it's a little bit hard to try and memorize all the common names, so we'll go ahead and focus on much more of the standardized names later. But the key feature I want you to focus on right now is that the more carbon atoms I have, the more of these sort of branching structures we can produce. And this means that my molecule can start having more and more configurations. If I throw on an extra carbon atom onto isobutane, I could throw it on one of these ends, or I could throw it on the middle, and that will give me different structures. And we need a way to be clear that both of these are butane, but they're not the same molecule. And we call these different configurations constitutional isomers, meaning they have a different structure, but the same molecular formula. These are more commonly known just as isomers. So if we want to go ahead and take a look at how you can have more isomers as you get to larger molecules, you can go ahead and see this as we go from, say, methane to decane. Methane, there's only one way to generate methane. It's a single carbon atom. If I've got two carbon atoms, they have to be next to each other. And propane, somebody's going to be in the middle and somebody's going to be on the end. So we only have the one structure. Once you get to butane, you can have two different structures. Pentane can have three. But once we get past pentane, you'll notice we quickly gain more and more configurations as there's 75 different ways to arrange decane. And this gets a little out of hand. So instead of trying to use these common nomenclatures like butane, isobutane, that won't work when we get to decane. So we need a much better way to name our molecules. And so we're going to try and name all of our alkanes with a given set of rules. So first, you're going to try and find the longest carbon chain in your molecule. This is going to serve as the base name. So if it's 5 carbons long, it's going to be pentane. Then you're going to try and find branching groups. Every one of the branching groups is called an alkyl group. And so we're going to give it a YL suffix or il instead of the alkane suffix. Then what we need to do is assign each of those substituents a number based on which carbon atom in the main chain it's attached to. So if we've got two substituents, the one that's larger, we're going to try and give the lowest number possible. Then what we're going to do is label each of these substituents based on which carbon's attached to and the name of the substituent with, again, that YL suffix. Now, if we got multiple substituents, so let's say I've got multiple methyl groups with 1 carbon long, then I'd either say di if I've got 2 of them, tri if I have 3, or tetra if I have 4. Then we're going to have a number with each, a numerical prefix for each of the places where one of those methyl groups is attached. Then we're going to list all those substituents alphabetically. So ethyl before methyl, butyl before ethyl, propyl right at the end. Now, this is a lot of rules, so let's try and give it a try. So let's try and name these 2 following compounds. So the first thing we need to do is try and find who's the longest chain. So if I started here, I could go 1, 2, 3, 4, 1, 2, 3, 4, 5. That's not bad, but I have a slightly longer one. 1, 2, 3, 4, 5, 6. So this means I've got a hexane. However, I left these 3 groups out on their own. Notice that they're all 1 single carbon, so I'm going to call them methyl groups. And I've got 3 of them, so I have trimethylhexane. Now, if I started with this as my beginning carbon, I've got 1, 2, 3, so 3, 3, 4. Or if I start on this end, 3, 4, 4. So we're going to try and minimize the numbers. So this is 3, 3, 4 trimethylhexane. So that's a lot going on. Let's try the other group. So trying to find the longest chain, I'm going to start over here. 1, 2, 3, 4. Both of these groups are the same, 5 and 6. So I've got another hexane. But now I've got much different substituents. So I've got a group here. This is 2 carbon chains, 2 carbon molecules atoms long. So this means I have an ethyl group. I also have 2 methyl groups here. So we've got to try and minimize that number on our ethyl group. So 1, 2, 3 ethyl, 4, 5 dimethyl hexane. And so that's our group. However, it's also important we can go the reverse direction. So let's try and build a compound for 2,3-dimethylpentane. So the big feature here is I've got a pentane molecule. So this means I've got 5 carbon atoms long. So 1, 2, 3, 4, 5. I have 5 carbon atoms long, and I've got 2 methyl groups. So this is going to be on 2 or 3. We can start on either end. So 1, 2, put a methyl group here. 3, put a methyl group here. And ta-da, we've got 2,3-dimethylpentane. And so we can use these same general rules to build most organic molecules. Now, let's go ahead and try and be a little clear of how I can reference these various groups. So I've got a whole bunch of different carbon atoms, but not all of them are going to be equivalent. So we try to reference each of these carbon atoms based on the number of adjacent non-hydrogen atoms. So for here, that's just the number of carbon neighbors. When we throw in some extra nitrogen and oxygens later, it will change a little bit. So when we're starting here, we're going to start with primary carbons. So these only have one non-hydrogen neighbor, or one carbon neighbor. So this guy's a primary, 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 primary. Secondary will have 2 non-hydrogen neighbors, so that will be these 2 groups here. Tertiary have 3, so 1, 2, 3. So this guy is a tertiary carbon. And then on the very end, the max number of neighbors you can have, a quaternary carbon, where you've got 4 non-hydrogen neighbors. 1, 2, 3, 4. And there you go. So this really gives us a good primer to alkanes. And these are going to really be, as we go forward, our basic building block where we can start as a framework to go to the wide range of all organic molecules. So next time, we're going to go ahead and add what are called some functional groups by adding in a couple of double and triple bonds into our molecule. Next time, alkenes and alkynes. Until then, take care.